highly scalable algorithms for maximum monomial agreement. Thank you very much.
Thank you. This talk is about using supervised learning, doing supervised learning via boosting, and particularly it's about using parallelism to find optimal weak learners from a particular class of weak learners. Now, Nina in the last talk yesterday gave a nice tutorial about boosting, and that's a good thing because I know almost nothing about it. We were just looking for an interesting example to test the scalability of our parallel branch and bound solver, and then by nice coincidence, this application fit the topics of this workshop. My colleague Jonathan Eckstein did all the lifting in this case, not just the heavy lifting. So for the input, we're given a binary matrix. The rows of the binary matrix correspond to observations, and the columns correspond to features. And then each of the rows is also is classified as in or outside of the class, a positive or a negative example. So for example, the rows could correspond to people, and the columns could correspond to their individual genetic traits or habits and symptoms, and then the class could correspond to whether or not they have a particular disease. Now they also have some weights, and I should say there's going to be a fair amount of notation here, but I know this is after lunch and everyone's going to be doing a faceplant soon, so I'm also going to try to say English for everything, even though I'll also have the math represented for clarity and for people who think better in math than in words. Okay. So we're actually interested in finding binary monomial. So binary monomial is better known in the computer science world as the clause of a SAT problem. So we specify a particular subset of the features that we want to appear in the positive sense, a particular subset we want to appear in the complemented sense. And we could then think of the binary monomial, if the xi's are binary variables 0 or 1, then it becomes binary function. So it's the product of the values of the variables that we want to appear as 1 or as positive times the product of the 1 minus the variables that we want to be negated or complemented. And so then we say that a monomial covers a particular vector if it agrees on all of the particular subpieces of this clause. So if it's 1 where it's supposed to be 1, if it's 0 where it's supposed to be 0. So here's a particular example using the matrix we had in the beginning. If we'd like x1 to be 1 and x2 to be 0, then J, the class of positive features, is 1, C, the class of complemented features, is 2, and in this particular case, the first and fourth vectors don't match that, but the other ones do. So that's how you pick out the covered variables. And the maximum monomial agreement problem is to try to pick out a subset of the features, positive and negative, that amongst the covered variables maximally distinguishes between the positive and the negative examples. So in this particular case here, in this particular example, if we want x1 to be 1 and x2 to be 0, we look at the 3 vectors that correspond to it, and we consider their weights. And we look at the difference between the weights of the positive examples and the sum of the weights of the negative examples. This particular one doesn't have much discrepancy. In fact, it's 0. But it was the only one that had more than one interesting coverage for 2 columns. So why are we interested in monomial agreement? It's because of a particular type of boosting that's based on linear programming called LPBoost. So the way that boosting works is you create a classifier from a convex combination of weak learners, which might not individually be doing much, but as a whole, in the proper combination, do a good job of distinguishing positive and negative examples. So you start off with nothing, and then you add a particular classifier and a weak learner, and then you figure out where your problems are. You add weights based upon where you are right now, and you just iterate until eventually you've added enough weak learners to have a good classifier. And LPBoost is based on solving this linear program where rho corresponds to the discrepancy or the distance that you want to have between the positive and negative examples. You're allowed to have some error, and there's a penalty in the objective function for that error where d tends to be small. This is the convex combination. So you solve this linear program Then you use the dual variables to weight the next set, and then the separation, which is actually a column generation, the way you find your next weak hypothesis or your next weak learner, is to solve this maximum monomial agreement problem. And we would like to solve it exactly because Goldberg and Sean in 2007 said that if you use an exact separation, at least in certain parts of the computation, rather than a heuristic, you tend to get better classifiers, at least in certain instances. So we're going to solve the problem exactly using branch and bound. This is a classic method that one finds exact problems for combinatorial problems, exact solutions to combinatorial problems. In particular, this is the way one solves integer programs in codes such as Groby or Cplex. We're trying to maximize a particular function over a set of feasible instances. Normally, this is expressed as a minimization problem, but because we're doing maximum monomial agreement, I'm going to switch everything and hopefully get it right in real time. So in a generic branch and bound solver, in order to customize it to the particular problem, you need to do a few things. The first is to come up with a problem representation. And then you have to define several different methods. You need to be able to create an upper bound, where given a set of feasible solutions that's represented in some compact way, you find a bound such that the actual value, in this case of the discrepancy, is guaranteed to be below that for anything within that subregion. You also have to be, it's generally a good idea to have a heuristic method, perhaps to round or to find a feasible solution from any particular instance. In particular, you need to be able to recognize a single solution, whether it's feasible or not. And finally, you need to be able to, given a particular subset of the feasible region, intelligently split it into, partition it into smaller pieces. So here's how branch and bound works generically. You start off at the root problem, which is your initial problem. You find the upper bound. That's the upper bound on the whole problem in the root. And you try to find a heuristic solution, if that's possible. Maybe it comes from the bounding procedure, maybe it comes from something separate, and if they happen to match, then you're really lucky, you found the optimal solution, you go home. And of course, that never happens. So instead, once you then instead partition the region into two subproblems, and then you recurse. And then, this of course looks like exponential growth, and it is, and it would be in the worst case, because this is the way you tend to solve NP-hard problems, and maximum monomial agreement is NP-hard. But there are four possibilities when you create these subproblems, only one of which is bad, even though this is the most common case, is that you just simply have to continue to recurse. You're not done yet. But it's also possible every time you divide this region, you add constraints to the subproblems. And sometimes those constraints are incompatible, so you could create an infeasible instance, which you can throw away right away. The other possibility is that you create a solution where the upper bound matches a feasible solution you found from that region, so you're done in that region. And alternatively, if you have an upper bound for the region that's worse than the best bound that you found anywhere in your search, then you know that nothing in it is interesting, and you can throw it away. That's called fathoming. And in order for this to work, in other words, in order for this tree to actually terminate in a reasonable amount of time, you need to have good upper bounds. One nice property about branch and bound is that you can always tell approximately how well you're doing, because the best solution you have in hand gives you a lower bound on the problem. And if you look at the set of open problems in the search tree called the frontier, if you look at the maximum upper bound, that gives you an upper bound on the whole problem. And so in general, you can stop the solution early if you have a relative gap that you're happy with, say 95% of the best solution. So now we're going to talk about customizing branch and bound to this particular maximum monomial agreement problem. And we found this was a particularly interesting problem because the serial code had already been done by Jonathan and his student, Noam Goldberg. So first you need to find a representation, and the representation is really easy. You just partition the set of features into four classes. The ones that have to be 1, that's J. The ones that have to be 0, that's C. The ones you can't use, that's E, the eliminated variables, and the ones you haven't decided on yet. And that completely partitions the set. So any partition is possible. Of course, they're not the same quality, but it has a nice property. And then furthermore, for any particular representation, this JCEF we can evaluate the objective function on this set J and C, and that will give us a feasible solution. And so this is a nice situation that doesn't normally happen for most branch and bound problems. And in particular, when the undecided class F goes to empty, then we only have one element, it's a leaf, and that's where you can terminate the search. So first of all, let's find an upper bound. So this F of E of JC was the difference between, or the absolute value of the difference between the covered positive examples and the covered negative examples. And so a really simple upper bound is just take the maximum of those two. Okay, so that's nice. But we can do a better job in branch and bound once we've decided, put some things in the eliminated set. We can be a little bit smarter. So in the eliminated class of variables, if we throw these columns out, let's say E is x2 and x4, and then do a radix sort on the remaining columns, the ones that are now equivalent, except for differences on the eliminated set, form an equivalence class. For each equivalence class, everything in that equivalence class is either covered or not covered. So we can treat them as a group. So let's see. There we go. So this is the notation here for, we were originally cared whether they were positive and whether they were covered. Now we additionally care what equivalence class they're in. So we break them up by equivalence class and whether they're positive, so they have to be covered, they have to be positive or negative, that's going to split them up, and then they also have to be in a particular equivalence class. So you can get a stronger upper bound this way. For each of the equivalence classes, there's a positive bound and a lower bound, and you take the highest of that, which means the weakest of that. So in this particular case, if this sum is positive, then we add it in, and if it's negative, we just have it as 0. That's what the plus means. And we can do this for the positive side, we can do this for the negative side. That doesn't mean it's achievable. That's why we have an upper bound, something that's easy to compute and that we know is a valid upper bound and is generally not achievable. But this allows us to leverage the eliminated class in order to get a stronger upper bound. Okay, and then there's a more convenient form here. A little bit of algebra we'll show you, which I'm not going to put you to sleep with here, is that you can start off with the original weak bound and subtract this min per equivalence class. And the reason that we express it that way is that it's relatively easy to compute this initial part. You're just doing repetitive intersections of sets that get smaller and smaller and tends to be fairly fast. So if you can fathom the problem that way, if you already know the upper bound is so bad that you can throw it away, then you don't have to do the more complicated second part of it. And if you do need to fathom it, then you can do the second part. Okay, so now, how do we branch? Well, it's really easy. That's another nice way of expressing it. If I'm in a particular node and I would like to partition the region, so here these are the ones that have to be 1, the ones that have to be 0, the ones that can't be there, the ones we haven't decided on. We pick one of the ones we haven't decided on, and we try it in each place. Try it as a 1, try it as a 0, try it as being thrown out. And this is the one that's most expensive to compute the new bound in because that affects the equivalence classes, and you have to recompute them. The Goldberg and Eckstein did consider larger multi-way branching, and this particular one gave better bounds and better performance. It created more nodes, but since we're going to be running in parallel on a massively parallel machine, extra nodes is actually a good thing for scalability, so we chose this easiest form of branching. So one other thing you have to do when you branch is decide which of the variables that are undecided you're going to branch on. So for this, we do strong branching. So for each of these possible f's, we compute each of these bounds. We put them in a triple, sorted by their value, and then we do a lexicographic sort, and we take the smallest one. And the nice thing about actually doing this is that it also gives us an even stronger bound that also depends on f, which is the minimum over all f of the maximum of these values. This is called the look-ahead bound. So we can also use that. It bounds the parent, and then all the children, the nodes underneath it, inherit that bound. Okay, so now that we've decided how we're going to implement these, we actually ran it in a system called PEBBL, our massively parallel branch and bound solver. Parallel stands for Parallel Enumeration Branch and Bound Library. We're going to talk about enumeration later. First of all, we're just going to talk about finding a single optimal solution. This is a distributed memory system. It's based over MPI, and it's uses C++ so that we can just use inheritance to customize for the particular problem that we're trying to solve. PEBBL was not the first, and it was not the only parallel branch and bound solver, but it's arguably the most scalable one right now. Okay, so one of the reasons that was really nice that we already had the serial implementation of the MMA algorithm is because PEBBL makes it so easy to take advantage of the heavy-duty parallel aspects of the code that's hidden within the C++ framework from the user. You can override a lot of things, but if you choose not to override it, if you have a decent debugged serial application, you can get up and running in parallel really easily because of this diamond hierarchy. So this is part of the core solver, this is part of the core solver. If you've got the serial application, you can create a parallel application by inheriting from both the parallel core and the serial application. And the only thing that you need to do is to create a function that tells you how to create a message buffer that holds the subproblem information and the basic global problem information. And within PEBBL, there's a particular data structure called a pack buffer I like to think of as a suitcase. You put it on your bed, you throw the things into the suitcase, you don't care about what the type is. At the other end, you just need to make sure you unpack correctly. Makes things very easy for starting things up. Now you can also take advantage of parallelism by doing some problem-specific parallelism if it's beneficial for your problem. I don't have time in this talk to go into all of the features that PEBBL has for doing fast parallel branch and bound. I will talk about a couple of them. In particular, because we want to run on very big machines, we do checkpointing. We do early output. That means that every once in a while you save the best solution you've found so that if the machine crashes or if you've been stuck forever at 3% and you set your bound at 2%, you can just stop with what you have. So there's also, because this is an asynchronous code, and there are lots and lots of processors and lots of various problems that are communicating with each other asynchronously, termination is challenging, and so I don't have time to explain it, but it does provably terminate correctly, and that was an issue for a while. Okay, so one particular problem that you have when you're doing a branch and bound tree and you have 10,000 processors is it starts at one node at the root. And if you have 10,000 processors, you have 999,000, 9,999 that aren't doing much at the beginning. So how can you take advantage of that parallelism until the tree grows large enough to be able to have the fairly obvious node level parallelism? So we have something called a ramp-up phase. And in the ramp-up phase, you allow all the processors to work together on a single node, and they grow the tree kind of in lockstep until you have a switchover. So there are a number of things you can do. You can do pre-processing if you have a kernelization operation. You can work on more difficult bounds than you would be doing on an individual processor. But in particular for the MMA, we do this strong branching. So at the root, where you have the most undecided nodes and you have to decide what to branch on, and the upper bound doesn't match the lower bound, of course, then you can take all of the undecided variables, split them evenly amongst the processors. If there's more than enough to go around, each of them individually computes the strong branching, basically, and then you do a parallel reduce to find the one that's going to do the best job of moving the upper bound, and then you also do another parallel reduce to compute the look-ahead bound. So, right, this is what we were saying. We're doing this. I just described it in English before I moved over to the slide. So then eventually, when there's enough nodes in the tree, you want to switch over to the, I guess you could call it the cleaner level of parallelism, where instead of working in parallel on a single node, processors individually process the nodes, because the tree is what's going to grow in an unbounded way. And so in general, there are ways that you can do that when you run out of parallelism, when the number of problems is large enough. In this particular instance, we do this crossover at the point where there are about as many open nodes as there are features, because that's about the level of parallelism that the strong branching has. And we do a perfect load balance. Because each processor has individually grown these trees in mirror, then they actually know which piece is theirs without having to do any communication. So it's perfect load balancing, no communication when we do this crossover. Okay, what PEBBL has, a hierarchical hub worker system. So each individual, they have a processor that works as a hub, sometimes as a worker hub. It has a number of workers it controls. That's a controllable parameter. There's also defaults for that. And then the hubs themselves have a tree for communicating for global information. The hubs only communicate these small tokens that allow them to locate the data of a particular problem, the bounds, just enough information to allow them to manage it. And then the other workers communicate the heavy amount of data themselves in what normally is a fairly random pattern. We have a lot of load balancing. It's really important that you do load balancing, because in the best of worlds, you would like your parallel computation to, as close as possible, match the order in which you explore nodes in the serial world. Normally in the serial instance, you take the open problem that has the highest upper bound, because within the bounds of your bounding function, you'll have to explore that anyway, because you can't throw it out until you open it up and look at it. You don't have any way to know that there isn't something interesting inside of that. Now, when you have a lot of parallel processors all going for a kind of a small amount of food there in terms of early nodes, they're all going to grab what's there, and they're going to start growing their own trees locally. If you aren't careful, and if you aren't lucky sometimes, you can create an awful lot of work that would never have been created in the serial processor. And in the beginning of parallel branch and bound, this could actually cause slowdown, where processors were slower by wall clock time than the serial process. We don't have that here, but you want to be very careful. So we have the hubs can sometimes pull workloads back from the processors, who keep a local pool to keep themselves busy. The workers, when they create create new subproblems, will occasionally randomly scatter them, as in the CARP load balancing algorithm. And then every once in a while, there's a rendezvous load balance where you go up and down the tree to share quality and quantity of workload, and then you do a rendezvous where processors that have work to donate meet up with the processors that have work who would like to accept work, and the ith donor and the ith receiver meet at the ith processor in a rendezvous. Okay, so here are our experiments. We did use the UC Irvine machine learning repository, in particular Hungarian heart disease, which has 249 observations, 72 features. There's also the SPAM data set. We dropped the missing features, and the ones that were real-time, we partitioned according to thresholds. They have these zeros followed by 1 instances, and the thresholds are correct if you don't bring two vectors together that should be separated. We ran on a really big machine. Each node has 8 processors, dual quad-core Xenons. The big machine has 22,000 cores and a lot of RAM. The general partition has a lot of cores, usually needs some special permission to get it. We didn't really need it for the examples that we were doing here. We had 128, a larger number of workers per core, because these are fairly hard bounding subproblems. So the first example, now this is the Hungarian heart, and this is the 253rd iteration in the LPBoost algorithm. The first set of experiments are dealing with was it worthwhile to ramp up or not. And so in this particular case, the ramp up is the red, and the non-ramp up is the blue. So it does make a difference. It runs out of parallelism here at about 512 processors, but by then it's running in about 10 seconds. So it's running fast enough. We see that the number of subproblems is fairly flat, so we're doing a good job of that load balancing. In the spam version, where we're trying to classify spam emails, we can parallelize to much further. And we run out of, we come off of the perfect speed up line a little bit after 4,000, And if you look at the number of subproblems, right around there is when it starts to go up a little bit. So we are having a little bit of extra work here. Okay, so in particular, we mentioned that ramp-up was worth it, that we generally, for these problems, could get down to 1 to 3 minutes. There was no significant loss between 1 and 2 processors, so there's not a lot of parallel overhead going from the serial to the parallel core in this instance, and there's not a lot of overhead going from one hub to multiple hubs. The next set of experiments involve parallel enumeration. This is also built into the PEBBL core, so you can specify enumeration in 4 possible ways: by an absolute tolerance, by a relative tolerance, by an absolute bound on the objective, and by asking for the k-best. So this requires an ability to branch through. If your leaf nodes have more than one instance, you have to be able to get that out of the way so that you can continue to grow the tree. You also have to be able to do duplicate elimination if you have a heuristic, because you might discover things from multiple parts of the tree once you start doing branch through. So we use a hash function for each solution to find a processor that owns it. That processor keeps a repository of solutions, and they're able to check for duplicates. In everything except the k-best, these repositories, everything has to be kept because you wanted everything within 5% of optimal. If you get 1 million solutions, that's your problem. You shouldn't have picked 5%. And so you keep these all independently, you just do a merge sort at the end. But for k-best, you have to do some communication up and down the tree to keep track of the cutoff point. We're interested in enumeration for this in particular because, remember, this problem we're trying to solve is a column generation problem for the LPBoost model. And normally when you do column generation, if it takes a lot of effort, it's worthwhile finding a bunch of good ones to add all at the same time. So in this particular instance, we find the 25 best and we add it in. That tends to accelerate the boost convergence. So here are the results when you enumerate on the Hungarian heart problem. This comes off of linear speed up a little bit earlier than it did before. That's because the problem it didn't get an awful lot more parallelism. There wasn't a significantly bigger tree, and the communication then, the extra communication for enumeration caused some trouble. But here in the SPAM 26, because the problems were significantly harder, the communication wasn't a big problem, and we scaled almost all the way down to 8,000 processors nearly perfectly. So this is all open source code. You can freely download it. That code has the knapsack examples as well as all the code for the MMA examples, and we'd be happy if people wanted to use that. So thank you very much.
Any quick questions? John?
When you enumerate the k-best solutions, is there any notion of distance between solutions? I mean, is it possible that your best few solutions are all very close to each other in Hamming distance or something? So they might not add as much to the boosting as
I think that
good solutions farther apart.
that's an important open question. So right now, I told you the 4 things that we allow enumeration over. There should be a notion of diversity. That is a difficult question. In this particular instance, you might be able to do something because Hamming distance and so forth makes sense. But for generic branch and bound, for example, million variable integer programs, that's a hard question. But I agree, it's something that you should be able to do.
Any other questions? Thank you very much, Cynthia.